So let's start. Thank you very much for coming to another seminar on Friday. Today we have another seminar, a special seminar like the previous week, because we will have two speakers that have been that were awarded with the JAE Intro Scholarship. That are some scholarships that are given by the SIC. In this case, in Medea, they are financed also by the María award. And so, well, today, like the past Friday, we'll have two speakers, and that is Esther Hoyo and María Pizarro, and they will talk about the work they have been doing with this scholarship in their master thesis. So there will be like short talks of around 10-15 minutes with some time for questions after each talk. So, well, they did a big effort to present today. So as last week, please make nice comments and constructive comments to the notes. So thank you very much. The floor is yours.
Hello, I'm Esther Hoyo, and I was awarded by a JAE Intro ICU scholarship for 9 months here at Medea in the master's group under the supervision of Pablo Chavala, who is working in behavioral and physiological assessment of fishes reared in aquaculture facilities. Today I'm going to talk about tracking behavioral and physiological responses of seabass in aquaculture cages. I want to start, well, the letter changed. I want to start talking about welfare. What is welfare? Welfare is defined as the state of the animal as it copes with its environment. It can be positive or negative, but it's important to note that these are not two discrete states. It is a continuum and can vary with time. How can we measure welfare? We can measure welfare with welfare indicators. In this case, I'm going to focus on the physiological and behavioral welfare indicators. For example, the heart rate of an individual, the spatial distribution of the individuals within the sea cage, the foraging behavior, social behavior, and swimming activity. In my high period program, I learned how to use 3 techniques, and I'm going to explain each technique. And I'm going to show you some results, but we are not going very deep in the results. The first technique I used was the acoustic telemetry. It consists in implanting an acoustic tag on the ventral part of the seabass, and this tag transmits a unique acoustic signal that is received by an acoustic receiver. In our case, we deployed 4 acoustic receivers in between the sea cages of the Linea facilities located in Fort and Dutch. And we got the data of depth and activity of the individuals with these implanted transmitters that we can translate to behavioral responses, distribution patterns, or even sometimes positioning. Not in this case, but sometimes you can position the fish. And what kind of data can we extract from here? We can extract the circadian rhythms. Here we can see a plot of the 24 hours of a day. The shaded zones are the night hours, and the white zones are the daylight hours. Here we can see the mean acceleration of the fish with the transmitter implanted, and we can see an increase in the acceleration during the hours of the day, daylight hours. But acoustic telemetry also allows us to have a long time series. In this case, we have here a plot that shows the six months from the end of June until November, and the mean depth of the individuals with these transmitters. And well, we can just see that the depth varies, but here at end of October, we can see there is a sudden drop in the depth, and the fish remain 2-3 days at 8 meters depth. And so we were wondering what happened here, and we correlated this data with the climatological data, and surprise, there was a storm here. So this kind of data can give us clues of how these fish interact with the climatological variations of the area. Another technique I used was the biologgers. That these are these tiny devices that are implanted in the fish in the heart next to the pericardium, and are capable to record the heart rate of the fish, the amplitude of the cardiac signal, the acceleration, and the internal temperature. And this can be translated to physiological responses, stress responses, or behavioral responses. Here, you can see an example of an electrocardiogram registered by these biologists. This is so beautiful, but it's not normal. Normally, we have lots of background noise, and it's a mess to clean and process all this data. And what information does the biologists give to us? We can also evaluate the circadian rhythms. In this case, it's a plot similar to the first I showed. But in blue, we have the heart rate, the mean heart rate of the individuals, and the mean acceleration. We can also see that there's an increase during the daylight hours. But biologists also allow us to assess the weekly patterns. Here we can, well, this is a plot of a 15-day period of time. And here we can see these variations, 24-hour variations. There's always a peak at midday, okay? But if you look at this heart rate line, you can see that here and here, there is no variation. The heart rate stays more stable. And why is this? Because it was weekend. And then we could assess how fish are affected by the human activities in the aquaculture facilities. During weekends at the Limia, there is nobody in the cages, so fish are more relaxed. And last but not least, we also use the 360 cameras to assess this behavior inside the cages. These cameras are able to record a video on the 360 angle, and then you can choose the frame you want to see. Here you can see a top view, a bottom view of the cage, one side, and you can unfold you can do like a panoramic view, and you can see all the cage. And this gives us information about the activity, foraging behavior, social interactions, or spatial distribution of fish in the cage. In fact, we are now working together with the data lab here at Medea and with the Polytechnic University of Madrid to try to automatize these videos to get automatically the spatial distribution of the fish. So to summarize, these three techniques I used during my stay here at Medea are useful to assess behavioral and physiological responses of the fish in the cages at different spatiotemporal scales. So we can know how the individuals cope with the environment, and therefore we can know their welfare states. Thank you everybody for your attention, and I would like to thank the
Thank you very much, Esther. We have time for questions.
I have one question. You mentioned that there are some periods of time where the heart rate doesn't have this daily peak, no? And then you said that it was associated to weekends.
Yeah.
No? But I wonder, those cages where the fish are in the sea or are inside the sea?
In the sea. Well, inside the harbor, but in the sea.
Okay.
Yeah.
So maybe it's not, because you said that it was maybe persons that were, if I understood well, there were people going at Limia, but in fact, these people outside in the bay.
Yeah, but
Maybe there are boats, there are differences in traffic of boats.
Yeah, but if there's more traffic of boats, heart rate should increase. Well, we thought that during weekends we do not feed fish, and this peak of heart rate is always correlated with the time of the feeding.
Or the feeding.
Or feeding, or crowding, or some like.
But then you didn't mention that.
No, I
That
didn't.
this seasonality in the heart rate maybe
Yeah, sure.
is driven by
Yeah.
a stimulus like that.
Yeah.
You are feeding at a certain point.
Yeah. Sure. In fact, we found that at 5 p.m. in the afternoon, we always had a peak, and we didn't know why. And it's that the touristic boat, like the bottom glass boat, passes like just near the gauges at 5. So yeah.
So, yeah, está como to check this, it will be maybe interesting to put an hydrophone or something to make sure the environmental noise.
Yeah, because in summer there's lots of traffic. Yeah.
Or indeed the receivers they have a, if you are using the thermal receivers,
Yes.
they have a noise,
Oh, yeah?
yeah, they record noise data. It's very rough, it just gives you an index of noise, but
Okay.
maybe you can try to correlate also changes in the heart rate with peaks of noise or something.
Okay, I don't know.
Any other question? I have more question because I think it's like science fiction, this heart rate. So how do you attach it? So it has, you have to put it close to the heart of the.
Yes, you do an incision here, like in the ventral part, and an incision here, and then you pass the biologer here,
Okay.
and bueno, lo coges, lo coges y lo fijas aquí, y le pones una sutura aquí y cierras la tal. Pero el problema es que dependiendo de la cantidad de grasa que tenga el pez, de la cantidad de musculatura, los datos a veces, pues, sobre todo porque también el corazón está muy cerca del opérculo,
Claro.
bueno, todo eso.
¿Y habéis visto si afecta al pez? Claro, porque normalmente cuando se operan los peces y solo haces una incisión y dejas ahí la marca en la cavidad peritoneal es como menos agresivo, ¿no? Que dos agujeros.
Sí,
Porque entiendo que entonces está agarrado por dos lados.
sí, está fijado aquí, y
Para que no, claro, porque se mueve dentro de la cavidad.
Exacto. Pero bueno, no, o sea, estamos de hecho ahora haciendo un estudio sobre, pues, según cómo lo coloques, los datos son mejores, son peores, cómo cicatrizan, según lo que le pongas. En fin, estamos en ello.
De todas maneras, a lo mejor haciendo análisis espectral puedes separar porque todo esto son cuestiones muy rítmicas. Entonces puedes separar la señal, por ejemplo, del opérculo por la señal del corazón. Ese tipo de señales en realidad es fácil, se puede hacer, no es... el problema es si estuvieras buscando cosas que son muy, muy irregulares,
Claro.
pero en los latidos yo creo que puedes separar esas señales.
Sí. También es verdad que estos loggers en peces no han sido tan usados, son muy usados en mamíferos sobre todo, tal, pero en peces no. Entonces cuando tú lo implantas a un oso, pues está mucho más, bueno, hecho para eso. Cuando tú metes el pez en el agua, que si mueve las aletas del opérculo, no sé qué, pues la señal. Pero
a los osos no se los meten
sí,
así.
más grandes los cacharros.
Bueno.
Pero sí.
Y luego hay que sacrificar al pez, entiendo, para poder.
Sí, bueno, a ver, podrías quitárselo, pero.
No es como los osos.
Bueno, pero tú puedes dejar el logger metido tanto tiempo como quieras y, yo qué sé, igual deja de grabar, pero yo qué sé, si tu estudio continúa tal, y luego ya lo recuperas.
¿Más preguntas?
Una pregunta siempre esto, que si necesitáis voluntarios para deshaceros de los peces una cantidad, yo me ofrezco.
Vale. Pues, thank you, Esther. Okay, so the next speaker is María. So, thank you, María.
So it's Maria, and I'm going to talk to you about the effects of hyperoxia on marine and aquatic ecosystems. So in standard conditions, dissolved oxygen in water is around 100%, which is known as normoxia. When those values are lower, it's called hypoxia. But when there's a superabundance of oxygen, we call it oxygen supersaturation or hyperoxia, which occurs naturally when there are high densities of photosynthetic organisms, which releases oxygen into the surrounding waters by doing photosynthesis, along with small water volumes. This usually occurs in tide pools, seagrass beds, kelp forests, shallow lakes, and streams. However, we can produce artificial hyperoxia by injecting pure oxygen into the water, which allows us to improve the quality of water and to avoid hypoxia during transportations, which is usually used in aquaculture. Hyperoxia has been reported to be beneficial to organisms. For example, some authors reported an increase in the resilience of coastal organisms to global warming, such as increasing their thermal limits. Others reported changes in their aerobic metabolic capacity, increasing their respiratory efficiency, and higher metabolic rates. Some of them reported an increase in their growth parameters. However, most of these studies are based on fish and to aquaculture, so we don't know so many information about the effects of hyperoxia on fauna. Neither we know ecological patterns. So what consequences does hyperoxia have on fauna? Are these consequences beneficial? And how hyperoxia could make it easier for organisms to survive warming water? So we will perform a meta-analysis based on the hypothesis that hyperoxia may have an important ecophysiological consequences across all taxa and could enhance adaptations to climate change. We defined 4 objectives. The first one was to determine whether hyperoxia could cause significant changes in species, to identify consistent responses across all taxa, to recognize information gaps, such as which are the most or the least studied taxa, and to identify if hyperoxia can expand the thermal limits of species under climate change context. To do so, we perform a bibliographic research on Web of Science with a list of the keywords you can see in the slide, obtaining a total of 1,071 papers that we screened, and we excluded 1,000 papers because of the irrelevant or unrelated topics. There were reviews, other meta-analysis, models, or whatever. And finally, the final papers must meet some criteria. For example, they must include an experimental setup, and they must report mean values, number of replicates, and variances. At the end, we obtained 49 papers that we are including in the meta-analysis. Once all data is translated to a datasheet, we analyzed it statistically with R with a package metaphor, which is a special package for meta-analysis. We use the HGG effect size measure to identify how the effect of the hyperoxia is happening. So it's a long formula, so we will talk about it later if you're interested. Once we found out the HGG coefficient, we plot it in a forest plot. When those values are positive, means that hyperoxia presents a positive effect on the organisms compared to controls, which are normoxia, which means 100% of oxygen saturation. When those values are around 0, it's a neutral effect, but when there's negative, so it's a negative effect of hyperoxia. To date, we have 39 out of the 49 papers included in our study. 3 of them present fluctuation treatments, and all the others are comparisons of hyperoxia compared to normoxia. And 22 of these papers have been published in the last 10 years or 15 years, which indicated an increase of the interest of the hyperoxia. So we expect to have 20 papers by the end of the decade. Once we plotted the HGG in the x-axis compared to the papers, which is in the y-axis, we have a positive effect in 11 papers and a negative effect in 6 of them. So, but this graph is not so much informative. So we compared the ecosystems. So we see an increase in thermal limits in both marine and freshwater ecosystems. For example, in the Gammarus pulex, which is a marine amphipod, the limit temperature was recorded in 37.5 degrees in hyperoxia, when in normal conditions it's about 35.1. While in marine ecosystems, there's an improvement in growth parameters. In freshwater is in metabolism response. If we compare life stages, we found out that adults and larvae shows the same benefits in their thermal limits and metabolism rates, whereas in juveniles, there's an improvement in their survival rates and in growth parameters, which is a good news for aquaculture sector. If we decided to difference between phyla, we recorded 6 different phyla, 4 of them showing an improvement in their thermal limits, which is good news against climate change. However, the only phylum showing improvements in metabolism is mollusca. And one thing that caught my eye was that chordates is the most studied phylum, but no benefits are reported under conditions of supersaturation. But this may change when we finish the meta-analysis because growth and metabolism parameters are almost positive. So to sum up, hyperoxia appears to increase thermal limits in marine and freshwater species, while better metabolic capacities are recorded only in freshwater species. And although hyperoxia has benefits in the 3 life stages studied, all of them differ. And among the most studied phyla are, among the phyla studied, annelids, arthropods, echinoderms, and mollusks present a higher thermal limits. So this means there is hyperoxia seems to be beneficial against global warming in many species. Mollusks are the only phylum showing metabolic benefits, but there are 2 other phyla very close to be significant. And oxygen supersaturation does not seems to be significant, as if to significantly affect behavior or genetics, growth, survival, or metabolic responses. And chordates are the most studied taxa without benefits recorded here, but there are still papers remaining to be added, so we expect to the results will vary slightly. So this is not the end. We have been working in another paper related to an invasive crab in the Mediterranean Sea and its raising rate and feeding preference. So if you're interested in crabs, stay tuned that we will publish hopefully soon in Proceedings of the Royal Society B. And I would like to thank my supervisor, Andrea, and the Agencia Estatal de Investigación to provide me this opportunity. That's it.
Thank you very much, Maria. So we are expecting another seminar soon, I guess.
María.
So any questions for Maria?
Dime.
Why does the hyperoxia affect, increase the thermal, how was it, the thermal?
El límite térmico.
Yes.
Bueno, realmente el límite térmico es la temperatura a la que...
No, pero ¿por qué es
bueno, al tener mayor capacidad de absorber el oxígeno, entendemos que te ayuda a adaptarte mejor. Si tú estás con, pongamos por ejemplo, un respirador, te es mucho más fácil adaptarte a los cambios del ambiente. Entonces, si tienes más capacidad de absorber oxígeno porque hay más oxígeno en el agua, pues te adaptas mejor a los cambios. Y en este caso sería el calor o la temperatura del agua. Dime.
Esta parte no entiendo muy bien o sea, al aumento de la temperatura del agua, si no estoy mal, disminuye la disolución de oxígeno, o sea, tiene menos cantidad de oxígeno. Entonces, ¿en qué punto habéis normalizado estos datos para saber cuál es la cantidad de oxígeno que hay a esas altas temperaturas? ¿No? Es como que el aumento que le estás proveyendo, en realidad, es que es una pérdida, o sea, que una de las causas de la mortalidad, etcétera, por aumento de temperatura es la falta de oxígeno.
Sí, bueno, esto ocurre en unos sitios muy determinados. Entonces, que es donde se ha visto donde ocurre la hiperoxia, que cuando se incrementa la temperatura, pues los organismos fotosintéticos realizan mejor la fotosíntesis y liberan oxígeno, pero es en sitios muy determinados como los tide pools, y en las praderas, por ejemplo, de Posidonia pasa igual. Entonces se libera mucho más oxígeno. Esto en el océano abierto no creo que pase. Son sitios muy determinados, que es lo que nos interesa ver. Por ejemplo, en las zonas costeras, como hay poco nivel de agua y muchos animales fotosintéticos, pues sí es mejor para los organismos o no. ¿Me explica?
Pero estamos hablando de porcentaje de saturación o de concentración de oxígeno.
Sí, es
Saturación.
Vale.
Sí,
Es que
sí, perdón, sí. Es el 100%.
Vale. Entonces sí, entonces cuando sube la temperatura se satura más,
Sí.
porque la capacidad de disolución del agua es más baja. Esto es como las botellas de champán, básicamente. Eso
Sí.
tiene sentido.
Bueno,
¿no?
de hecho-
Porque las decías, hay menos oxígeno, pero hay más saturación.
Claro, entonces, por ejemplo, aquí mismo lo puedes medir. En verano estuvimos midiendo y es que al lado del puerto tienes una saturación superior al 100%. Eso no quiere decir que luego pues, la concentración sea inferior.
También una cosa que cuando es en esa temperatura de control experimental, es que tienes la misma temperatura, manipulas el porcentaje de oxígeno a la misma temperatura y ahí es donde tienes una normoxia y una supersaturación de oxígeno. ¿Vale? O sea, las comparaciones siempre son hechas en pares, en las mismas condiciones. ¿Vale?
Cuando hablan de metabolismo, ¿qué variables se utilizan en los trabajos?
Hay una lista muy larga. Como al final no podemos usar las 150 variables que me han salido, hemos decidido agruparlas. Pero esto es muy preliminar, porque en metabolismo tenemos como 80 variables, entonces es probable que las terminemos separando. Dentro del metabolismo hemos incluido, por ejemplo, la cantidad de hemoglobina que hay, que se mide, la cantidad de oxígeno, la eficiencia de respiración, etc. Yo creo que al final terminaremos separándolas, porque dentro de la categoría metabolismo hemos añadido variables muy dispares.
Hay trabajos que hayan mirado estrés oxidativo, actividades enzimáticas asociadas.
Sí,
con
hay
esto,
trabajos,
o de la sobresaturación.
sí, hay pocos, pero 2 o 3 hay que miden el ROS y la actividad enzimática. Hay alguno que mide la cantidad de proteínas que generan bajo el estrés de la cantidad de oxígeno que hay. Es una pasada. Pero claro, es una lista muy larga, entonces estamos viendo cómo podemos agruparlas para que no sea tan dolor de cabeza. Pues hemos diferenciado entre supervivencia y límites térmicos porque los límites térmicos estaban asociados a una temperatura. Eran las variables la Ctmax, que es la temperatura crítica máxima, y la LT50, que es la temperatura a la que la mitad de los individuos se mueren. Y la supervivencia, pues, vive o se muere. Y esas estaban relacionadas con la temperatura.
¿Preguntas? Vale, pues lo podemos dejar aquí. Muchas gracias.